So yeah, my name is Alex, Senior Dev Engineer at NVIDIA. And for the last year or so of my life, I guess I've been working primarily on stability and helping developers sort out some sort of stability issues with Tile, specifically focusing on GPU crash issues. And that's where Aftermath was kind of born out of. And I'm going to be talking today about some of the advances we made since last year at GDC when we first proposed Aftermath to everyone. And yeah, we'll go from there. So why did the GPU crash? It kind of sounds like the beginning of a bad joke in a lot of ways, which I guess is somewhat symbolic, as I'm sure you're all painfully aware for the state of affairs where we were last year with regards to this topic. I hope you're all aware anyway, at least. So being a bit more specific, what is a GPU crash? I'm sure you're all aware, but just for covering all our bases here. I'm talking about this thing. So it goes by many names depending on OS and API that you're using, but TDR, timeout detection, recovery, hang, device removed, crash, they're all kind of lumped into the same bucket. And as a developer, all you really get back is, that's what's happened, and that's it. Not a whole lot more. And yeah, you may be familiar with this thing, depending on OS or whatever, but the screen might flash a few times, or this bubble will pop up, and you're done at that point. It's a dead end, right? So taking a look behind the scenes a little bit, what's actually going on there? I don't know how many of you know, but just, again, for completeness, we're going to talk about it. So basically, OS, GPUs, driver, they all schedule command lists, buffers, whatever, for execution on the GPU. And then at some point during execution, something happens. It might be a fault. Could be a long-running shader, an infinite loop, poor synchronization, anything like that. And basically, this occurs, and the GPU scheduler or the driver or whatever then goes, no, nothing's happened for the last X seconds. The default is 2, by the way, for Windows. But it's configurable again as well. But this happens, and the OS then raises the appropriate bug check. It does its thing. The KMD attempts to reset the engine or adapter that the fault has occurred on. And what generally happens is that the device is removed, or way worse. This can also end up in a blue screen, or end up in that kind of situation. It's not good, right? So what can you do, really, to detect these situations? Before Aftermath is essentially just pay attention to return codes from the API. So quick walkthrough of what happens there. Crash is detected, like we just went over. And basically, it's detected from the CPU by one of the return codes from an API. It may return like DXGI, device removed, device hung, or the Vulkan equivalents. And from that, you can kind of know that the crash has been due to some commands that have happened in the last n frames or so. Typically, the GPU, the driver, buffers up a number of frames in flight, so you can kind of assume that in the last n frames the problem has occurred. And from that, you basically know that the CPU call stack is essentially worthless, and none of this at all is useful for debugging in the slightest. So this is a common problem from everyone. You're not alone. And working with as many developers as I do, this is a common ask or request for help in this situation. And so that's essentially where Aftermath began. So quick elevator pitch. What is it? It's the post-mortem GPU debugging tool. It allows you to get more information back from the GPU after a crash has occurred. The purpose of that is to help you diagnose and fix GPU crashes, TDRs, whatever. And one of the cool things about it is we have made it fast enough for you to be able to ship it in a game. And what's cool about that is if you're already doing uploading of crash exceptions, if you have some sort of handler for that kind of thing, you can also include the information you get from this tool in those dumps so that you can mine and farm a lot of data from many people. And what's interesting, version 2.0, which is not out yet, currently we're on 1.3, but we're making a big jump to 2.0 very, very soon, and that's going to be available shortly after GDC. As far as support goes, the graphics API, currently supports DX11 and 12, but with 2.0 we'll also be supporting Vulkan. I'm sure many of you are happy about that. And of course, the platforms we support, it's specifically a GeForce tool. It does require a lot of driver-side stuff, so that's why it's sitting there for now. But platforms, Windows, UWP, if you're using that, and Linux, and 86, 64, whatever you're developing games on. So there's quite a broad spectrum support now. So I'm quickly going to run through the features and basically what it does for you from a programmatic standpoint. So this is the feature list. I'll go into more detail in each of those shortly. The ... at the bottom does mean that more stuff is coming. It's just, how these things go. It's just not quite ready yet for this presentation, unfortunately. But there is more stuff coming. So quickly going into the reasons for crash, which is one of the features that we support in the API. I'm sure as you're familiar, again, that if you call getDeviceRemoved reason or other APIs from the graphics sense, then you get a very vague or general errors. Usually it's something like device removed or device hung, device timeout. It's generally not very helpful. What those actually break down into is multiple different kind of categories here. And I feel like, having worked with a lot of developers and seen a lot of crashes in the last year, that most of these boil down into two categories. Essentially, you have faults, which are on the right, and those are things like page faults, which are more common in like DX12 low-level APIs, where you have to manage residency yourself. Invalid page accesses, which they're essentially the same as page faults, but they tend to spawn more from cases where you have reads of memory or accesses from memory, where you're expecting one kind of memory, but actually the backing memory says it's another kind of memory. So you also end up with a fault in this scenario. Push buffer faults, which typically happen when you ignore the return codes that are coming back from the API. So like you may have a failure to create a specific thing, and what that ends up doing is it ends up passing in some circumstances, but down the line that will end up crashing. And graphics exceptions, which are just general graphics engine exceptions on the hardware. Those things typically seem to be stuff like unaligned constant buffer views. They have this 16-byte alignment rule. So when you ignore that, you end up with a graphics exception. It's not necessarily a fatal one, but then what can happen there is that can lead to fatal exceptions down the line. And then, of course, timeouts, which have been around for much, much longer. It's typically stuff like incorrect synchronization, having fences which always wait on something that never really is signaled, and like infinite loops, long-running shaders, that kind of thing. What's interesting, though, is that the way we handle a lot of these fatal faults on the right is just by killing the engine that we get them on. So we get a return code from the GPU in our kernel mode driver, and depending on the engine they're emitted on, we might just say, kill that engine. And what happens there is that the OS watchdog mechanism kicks in for TDRs, and we just ultimately end up doing a TDR. But really, it's because we induced that TDR. So how do we expose this via the API? Get device status API that's currently in there actually already. And these are the possible statuses that we return. It's not quite as broad as this last slide, but we're working on improving that. But basically, you can consider page faults to be invalid page accesses, page faults, and grouped into that one single call. And DMA faults is the mapping for the push buffer faults and graphics exceptions. Timeouts should be self-explanatory. The rest are sort of like transition stages. And unknown shouldn't really happen, but it's there anyway for completion. So one of the other features we recently introduced is something called resource tracking. It's specifically there to address the case of page faults. So it's more focused towards the lower level APIs, although it's still possible to do in DX11 and whatnot as well. But it's there for DX12 just now, hopefully Vulkan soon. And the idea behind this is that since we have access to the faulting virtual address, and we also have access to all the resources that were ever created by the application and the driver, we can essentially build this table at the bottom here on every resource creation and release and map that. And then at fault time, we can do a reverse lookup. So you can consider this crude block on the right-hand side to be a rough diagram of video memory. I'll give you a quick example of how that works. So for instance, if your application comes along and releases or evicts a buffer from video memory, we'll track that. So the table is updated with a 1. It's kind of hard to see in the table there. And then when the application or whoever accesses that buffer, that will ultimately result in a page fault. Maybe it's this random offset address. It could be any of the addresses. And what we then do at fault time is then we go and look up that table, literally iterate over it. We have a lot of time at TDR time. There's no expectation of performance there. We look up that table to figure out which actual resource the application may have faulted on. We're finding this is really useful for DX12 applications in particular, and hopefully this is something we port over to Vulkan in the future, but it's not quite there yet. But this is something that we rely on pretty heavily, and it's exposed to you now via Aftermath also. So hopefully you find it useful too. As for the actual implementation, it's really one call after TDR. This page fault info structure, this basically contains the virtual address, the page fault kind of code, and also the resource descriptor. So you can imagine if you've released the resource, we may not want to just return the pointer to you. So what we also return is like format, dimensions, MIP levels, array size, like anything we can do to help you identify the resource. But also if you are able to, if you do want to get the application pointer back as well, which isn't going to help you if it's been released, right, because that memory is gone. But still, you can register and unregister the resources as you like, which basically hooks up the driver handles with the application resources. That's how we enable that mapping for you. One of the other features that's been around there since the beginning of Aftermath, it was kind of the start of Aftermath, was the ability to insert super low overhead markers into the command stream from recording time. And then what that allows you to do at the TDR time is read back those markers last read from the GPU. So basically, the API allows you to insert these markers, and then what this does on GPU execution is it will go through each of these markers and check them off as it reaches them. And then a crash happens, and you know the CPU location because you can read the return codes from the API. And what that allows you to do is essentially say the difference between these two must have been roughly the location when the GPU crashed. So it allows you to narrow in, if you remember from the earlier slide, you have like n frames of possible commands that happen on the GPU. It allows you to narrow right in on within the granularity of the markers that the application sends out, which is obviously a massive narrowing in, depending on how many markers you emit. But so from an implementation standpoint, we have this API. It allows you to hook up any application data, contextual data within the command stream, be it a command list or a deferred context or a command buffer. We allow you to do that from the API. And then after the device has been removed, we can allow you to call getData and return 2 markers back, which is something new we're adding in 2.0. And basically the idea behind that is that we allow, for each marker that you set, for each checkpoint that you set, we actually emit 2 markers on the GPU. One at the front end of the pipeline and one at the back end of the pipeline. And the reason for that being is that the GPU is this hyper-parallel, hyper-pipeline machine. And having just a single marker it doesn't really fully represent the workloads that could be happening in the GPU. You could have out of order execution, you could have draw calls overlapping each other, just depending on how the work was scheduled. And so this is what that helps with, right? So you the top end marker is work entering the GPU, bottom is the work exiting the GPU, and from that range, you can determine which workloads we're actually executing on the GPU at that given time, which does help you narrow in significantly. Vulkan, I'm sure many of you are pleased to know that we're adding this functionality support to Vulkan itself. It's not going to be part of the Aftermath API. We're releasing it as a Vulkan IHV-specific extension, at least initially. And it's just basically the checkpoint marker model that we're also releasing initially, but we do plan to support the other features as well, as we see fit. There's some differences between the memory model between Vulkan and DX12, so some of it may not be directly applicable, but yeah, we're going to start here and we'll go from there. A lot of developers have been asking for it, so hopefully you're going to find that useful. If you do need access to it, it's going to be available via the usual means for getting access to beta development features, and the link's up there. You can check it out after. Another thing the Aftermath does support is the new ray tracing APIs, DXR, that's been coming out. We're finding that a lot of developers are experiencing TDRs and the same kind of problem that you would expect with the other APIs. There's no special case here. And so we do support DXR and ray tracing from Aftermath. One of the caveats, I guess, there, though, is that the trace dispatch rays, I think is the API call, it does have the ability to spawn potentially thousands or more shaders, and you never really know which one gets executed in a given frame. But the checkpoints mechanism only really allows you to link back CPU contextual information to the GPU command stream. So you kind of have this same problem, I guess, that you would have with execute indirect or something like that. But that is something we're addressing in the future, and it should be available for 2.0. It's just not quite ready to speak about yet, unfortunately. We tried, trust me. But the resource tracking, the GPU device status information, that all works and is compatible with DXR as well. So hopefully if you're stuck on DXR, TDRs, this can help you out as well. So I've been talking a little bit, mostly about the actual functionality and how it works, but really what does it do for me? Well, there's a little bit of a preconception that it just kind of gives you the answer, I find. But unfortunately, as much as I would like that to be the case, it's unfortunately not. You have to really know what the data is telling you in order to make informed decisions about where to go next with debugging. And I'm going to cover a couple of these here. So for example, like checkpoints, they don't necessarily tell you which workload caused the crash, and resource tracking doesn't necessarily tell you which resource caused the crash either. What they actually tell you is that the checkpoints tell you where the workloads, what the GPU last finished processing before a crash. It's not necessarily the actual thing that caused the crash. Depending on the granularity of your checkpoints as well, your mileage is going to vary there too. So it's worth considering. For resource tracking as well, there's a special case in DX12 where because there's this separation of binding to the descriptor heap and actual having resources resident in memory also, you can have this weird mismatch thing. So you can imagine a case where you've released a resource, and that's valid, but you've accidentally left your descriptors stale in the table, which are still pointing to that resource. And then you may get a page fault there if your shader looks up that descriptor offset. But you validly released that resource, and it's going to point to a weird resource that you're not quite sure how it ended up there. So on top of Aftermath, I do encourage some additional validation and verification in the engine for looking at this kind of problem. It's not solid. This is definitely what it is, but it does help you kind of move in the direction of getting a fix. So like I said, worked with a lot of developers over the past year, a lot. I think over the past year since last GDC, my email filter folder for Aftermath is around about the 6,000 mark. It's a lot. And over that process, I've kind of developed my own guidelines and actual debugging process that I think you might find helpful. I hope you find it helpful. It's not always obvious. This thing's kind of new, so I think it's worth sharing with you guys. So what I would recommend doing is to just collect as many crash dumps, as many crash data scenarios as you can for a particular repro. And then the idea is that you want to try and find some commonality between them. I mean, it's hard to just even on the CPU, debugging like a driver issue, it's hard to do it from just one single crash dump. It's a super pipeline system. The fault may happen way downstream when really it was data upstream that was passed down. So collecting as many different cases and as much data as you can on a single repro is vital, I would say. And once you have all the information, the idea is to collect and figure out what the commonality is between them. And that is also not entirely obvious. So there may be things like same shader, same resource, and you can kind of determine that fairly easily, I would say. But also, for instance, some of the cases I've seen is like, use the same function library for specific shaders, and many shaders reference that library. Like forward plus is a common example. Tile, like any of those things would be very similar, right? And it's the same block of code, but it's reproduced inside many different shaders. And that's one of the gotchas to watch out for. And typically what I find actually helps there is to look at a capture in Insight, RenderDoc, Pix, whatever, and have a look at the actual assembly that's going on. Because I feel like from that level, everything's flattened out. All the contextual information's gone, and you can kind of see, oh, there's a loop there that's like, oh, it's the same as the loop over here. And you look at the HLSL, reference it back, and you can see, oh, there's a case where that could be infinite if the data wasn't validated on entry. And of course, once you have all the information, it's just simply a case of dividing and conquering all those common factors, stripping part of it out, adding extra validation here, all that kind of thing. And it's a very simple process. But if you follow this, you can get down to a fix, I think, fairly quickly, in my experience. And of course, I learned all this the hard way, so hopefully now you guys can benefit from that. But I'm still willing to hear from anyone or you guys if you still have issues that this doesn't quite solve. But still learning as well. This is a new kind of thing. I did touch on it earlier, but Aftermath is fast enough to be shipped in an actual application. So one of the benefits from that is if you want to do that data gathering process, it could be done if you have the system or the capability of allowing your end users to upload crash dumps. You can include that information there. One of the also neat benefits I would say you get from that is that then you have the ability to bucketize crash dumps based on their signature, which allows you to group them by priority and frequency. So you can attack the problems that your end users are seeing the most and are perhaps the most annoyed about. And if you don't have that system, then of course the same thing applies for your internal QA. I'm sure you know. So what else is there? When we last spoke, it would have been Aftermath. But it seems now like there's a little bit of a shift in focus for this kind of thing within the industry. So I'm just briefly going to cover these things. You can go and look them up, reference them after, or whatever. But it was a great talk by Sean Hargreaves and Bill Christensen yesterday from the Microsoft team. They're looking at they've added support for this in PIX, I believe. It literally allows you to programmatically initiate a capture from your game and then open it up in PIX after, so you can see the whole frame that led up to it. They're also improving the support for the DX debug layers and the GPU-based validation, GBV. They're always improving that, iterating on it, improving it. And that's more of a preventative measure. Like you can think about maybe in your studio, you could have a machine just running GBV and running the game, so you're constantly catching these things overnight. It's more of a preventative measure, but that's also there. We worked alongside Microsoft to get the write buffer immediate API, which is basically exposing the Aftermath marker style API checkpoint stuff that we already expose. And that's available via just DX12 vanilla now. And of course, Aftermath 2.0, let's not forget. And in the future, watch this space. There's still a lot more to happen here, a lot more collaboration. There's a lot more features. There's more coming in 2.0 as well I haven't been able to cover. But also just in general, there's a lot more coming. We know that there's a gap there between what the expectations are and what the reality is. So that's being worked on. And that's me wrapping up. Hope you enjoyed.